All right, we're going to talk about theorems about roots of polynomial equations. So we're going to talk about the rational root theorem. We're going to talk about Descartes' rule of signs and the conjugate root theorem. Okay, so if I have a polynomial, p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a to the first times x plus a sub 0. I can actually find my possible rational roots by finding the factors of a sub 0 and the factors of a sub n. So it's the factors of a sub 0 and the factors of a sub n. So when we're going to do this, we're going to talk about p, we're going to talk about q, we're going to talk about p over q. Okay? So here we are, what are the rational roots of 2x cubed minus x squared plus 2x plus 5. So I could just start by picking numbers and plug them in there and see if I get 0. Not very efficient. So what I'm going to do is I'm going to come here and I'm going to go p. So this is p and this is q. So I'm going to find the factors of p. Well, the factors of p are plus or minus 1, plus or minus 5, right? So those are the only factors of p. So then I'm going to look at q. And I'm going to find the factors of 2. So that's plus or minus 1, plus or minus 2. Now I'm going to go p over q. So I'm going to take the values of p and I'm going to put them over the values of q. So I start by going 1 over 1. So 1 over 1 is 1. 5 over 1 is 5. Now I'm going to go 1 over 2 is a half. And then 5 over 2 is 5 halves, okay? And so now I've actually limited this to actually only 8 values I have to plug in, all right? And there are some shortcuts to finding those. So one of the things is, so I'm going to use synthetic division to find these factors out. So, or you could just plug them in, it's pretty quick. So I'm going to use synthetic 2 minus 1, 2, 5. If I plug in 1, we'll just be efficient here. 2, 2, 1, 1, 3, 3, 8. 1 is not. There is a shortcut to determine if 1 is a factor. All you have to do is add up the coefficients. If the coefficients add up to 0, 1 is a factor. Okay? If I negate it, it would be if the negation of this works. So I'm going to change all the signs here to see if negative 1 works. So now I'm going to test negative 1. So 2 times negative 1 is negative 2, negative 3, 3, 5, negative 5. That's good. So 0. So negative 1 is a root. Now, negative 1 could be a root again. Or I might not have any other possible rational roots. So we're going to test negative 1 again because it might have multiplicity. Okay? And then once we get this down to 2 numbers, that's a linear binomial. So then we can just kind of set it equal to 0 and solve. So this becomes negative 2. This gives me negative 5. This gives me 5. Oh, it doesn't work. Okay? So negative 1 only works once. Okay, so now we've already done 1. We don't have to redo 1 because if it's a factor, it doesn't matter where you do it in the synthetic division, it would have to work out. Okay, so now we're going to try a half and see if a half works. So this is a half, so that gives me 1, negative 2, negative 1. That doesn't work. Okay. We could try a negative a half to see if it works. That would give me negative 1, negative 4. No, it still doesn't work because that's going to give me positive 2. Okay, so halves don't work. So now we're going to try 5 halves. Okay, so 5 halves times 2 is 5. This gives me, 2. So this gives me 5 again. Oh, that's 10, doesn't work. So the last one we're going to test is negative 5 halves. If negative 5 halves doesn't work, the -1 is my only rational zero, okay? So the others are going to have some kind of radical, okay? It may be imaginary, it may not. So this gives me -5, this is -8. So negative times a negative is a positive, okay? So that gives me positive 40 over 2, which is 20. It doesn't work, okay? So my rational zero would be -1, okay? But it gives you a starting point on which numbers to plug in, all right? So we're going to do that one more time, and we're going to do it up here for 15x cubed minus 32x squared plus 3x plus 2. And we're going to find those zeros, okay, so those roots. So the first thing I'm going to do is find the factors of p. Well, remember, this is p, this is q, okay? So the factors of 2 are plus or minus 1, plus or minus 2. I now go to my lead coefficient. I'm going to factor it. Factors of 15 are 1, 3, 5, and 15. So now I'm going to go p over q. So 1 over 1 is 1. 2 over 1 is 2. I will usually, personally, I'll usually just go these over this one first. I'll kind of work through and then put them out here. And sometimes I'll put them in rows if there's a lot, just to make it work out easier for me. And you don't have to rewrite roots. So what I mean by that is if I had 2 over 1 is 2, but if I had 4 over 2, I don't write 4 over 2 and write 2 again. It's just once there, okay? So now I have 1 over 3. I have 2 over 3. I have 1 over 5. I have 2 over 5. I have 1 over 15. And then I have 2 over 15. So this one ended up, the more factors you have, the more possible zeros we have. So I have 2, 4, 6, 8, 10, 12, 14, 16 possible zeros, rational zeros of this, okay? And so I'm going to start using synthetic division. The nice thing is once I get this down to x squared, I can then look at factoring, or I could look at the quadratic formula instead of working through the rest of these, kind of as a guess and check. So let's look at this. So 15 minus 32, 3 and 2, okay? So usually I'm pretty, there's another, at the end of this lesson, we'll talk about, there's actually a way to eliminate about half of these values to figure out where you're going to start. So 1, 2, so I would probably start with the negatives just to kind of have a starting point. But we're going to kind of work through these as just as a elimination. So we'll start with 1. So, and then once we get to a point where we know it's not going to work, we're going to stop. So this gives me 15, negative 17, negative 17, negative 14, negative 14. 1 doesn't work. So let's try negative 1. That gives me negative 15, negative 47. This looks like it's already going to be too big. 47, 50. Yep, going to be too big. Okay. So now I know 1 and negative 1 don't work. So those are not going to work. Those are not rational zeros. So now I'm going to go to 2. So this gives me 30, negative 2, negative 4, negative 1, negative 2. Okay. So now I know 2 is a factor. Now I'm in a quadratic, right? 15x squared minus 2x minus 1. Are there factors of 15 and negative 1 that when you multiply together have a difference of 2? Okay. Well, there are. So it's 5x plus 1 and 3x minus 1. Okay. So I now can factor this because I have it in a quadratic. I could have put it in the quadratic formula. So what's going to make that 0 is negative 1/5. What's going to make this 0 is 1/3. So there are my 3 zeros. Okay. The idea is to work smarter, not harder, right? I mean, if I would have went through this, eventually I would have gotten to 1/3, right? It would have been 2 sets away. Not too bad. Okay. And then I could have pared it down. But if I know that this factors right here and I can see that this factors, I might as well use that knowledge. Okay. So that's using the rational roots to find those zeros. Okay. Now the conjugate root theorem. So if you remember what a conjugate is if I have a radical, it doesn't matter if it's a radical of a positive number or a negative number, it's just a radical. Conjugates are the opposite signs of that radical. So a plus the square root of b, the conjugate would be a minus the square root of b. And a plus bi and a minus bi. So if a plus the square root of b is a root, then a minus the square root of b is also a root. Okay, so square roots always come in conjugate pairs. If a plus bi is a root, then a minus bi is also a root. Okay, so what that's saying is if I have the square root of 2 and 1 plus I are roots, what are the other 2 roots? Well, this is positive square root of 2, so I have to have negative square root of 2. And this is 1 plus I, so I also have to have 1 minus I. So there are my 4 roots. Radical roots always come in conjugate pairs. Okay, always, 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 always. Okay, so here it says, what is the 3rd degree polynomial with roots -4 and positive 2i? Well, right now we only have 2 roots. We have to get that 3rd root. Well, that 3rd root is -2i, right? Because that's the conjugate root. So now I have x minus 2i, x plus 2i, and x plus 4, right? Because it always goes in opposite sign. Well, I'm going to multiply these out first, okay? So now I'm going to go x times x is x squared. X times 2i is plus 2ix. Negative 2i times x is minus 2ix. And then negative 2i times 2i is negative 4i squared times x plus 4. So now I'm just going to rewrite that down here, simplified. Notice my 2ix and my negative 2ix cancel out, so this gives me x squared. If you remember, I squared is -1, so I have -4 times -1, which is positive 4 times x plus 4. All right? Now I can go ahead and multiply this out. X squared times x is x cubed. X squared times 4 is 4x squared. 4 times x is 4x. And 4 times 4 is 16. There's my trinomial with factors of -4, 2i, and -2i. Okay, so I can multiply that all out. The last thing we're going to talk about is how to kind of look at this and determine how many possible rational zeros we have. How many possible positive rational zeros and negative rational zeros we might have. Okay? So it says, this is Descartes' rule of signs. So Descartes' rule of signs says that if I want to know how many possible positive real roots there are, it is equal to the number of sign changes of p of x, or is less by an even number. Okay? So I'm going to take the sign changes of p of x, and that's going to be my positive roots. Okay? My negative roots is equal to the number of sign changes of p of negative x, or is less by an even number. Okay? So what that will, you'll see me do a lot of this. So positive roots, negative roots, and all this is doing is telling me the possible number. Okay? It doesn't tell me if they're rational or radical. It just tells me that the possible number, okay, how many there are going to be. So what I'm going to do is I'm going to count how many sign changes there are. So this is a positive x cubed. So positive to negative, did I have a sign change? Yes, that's 1. Negative to positive, that's 2. Okay, so now I have 2. So it says is equal to the number of sign changes of p of x or is less by an even number. So 2 or 0. Okay, so essentially what's going to happen is this number is going to be subtracted by 2 because we have our conjugate root theorem, right? So it's always subtracted by 2 and I keep every single number down to until I get to either 1 or 0, okay? So this would be 2 or 1. Now, if I plug in a negative x, that's going to give me, so if I have negative x cubed minus negative x squared plus 1, that gives me negative x cubed minus x squared plus 1. Do I have a sign change here? No. Sign change here? Yes. So I have 1 negative root. Now, if I wanted to know that negative root, okay, that's the where I'm going to start with my rational roots. I'm going to start with the negative numbers because I know I have one. This does lead us to the imaginary roots. So then I will have imaginary, okay, or complex, all right? So our total roots is 3. So my positive plus my negative plus my imaginary have to add up to 3. So 2 plus 1 plus what will give me 3, 0. 0 plus 1 plus 0, 0 plus 1 plus what gives me 3, 2. So my imaginary roots would be 0 or 2, okay? Let's do this one more time with a little bit bigger function. So let's say p of x equals 5x to the 4th minus 3x cubed minus 6x squared plus 4x plus 5. Okay? Now, and I'm going to put here p of negative x so that way later on we can get it. So I have the positive. So if you struggle with knowing how many total roots there are, and we're going to talk about that, I think, in the next section, but it's always my power, my degree. So positive roots, so I count the sign changes. Positive to negative, that's 1. Negative to negative, didn't change. Negative, positive, that's 2. So I have 2, and then I'm going to subtract by 2, or 0. I've gotten to 0, so I'm done. So negative roots, I'm going to take in, plug in a negative x. So the nice thing is I don't have to do a lot of work. All I have to do is look at my odd powers and change the signs of those. So this becomes 5x to the 4th plus 3x cubed minus 6x squared minus 4x plus 5. Okay. I now count the sign changes. Positive to positive, no. Positive to negative, yes. Negative to negative, no. Negative to positive, yes. So I have 2. This is, I can subtract 2 from it, or 0. Okay? So you might have a lot. Let's do one more. Let's get it kind of big. Let's go 5x to the 5th minus 4x to the 4th plus 3x cubed plus, let's just alternate back and forth. So that way we can kind of see. So positive roots. So 1, 2, 3, 4, 5. So I could have 5 positive roots, or 3, or 1. Okay, so there's all these possibilities on the roots. So negative roots. So these all become negative. So negative, negative, negative. I would have 0. Right? So if I had p of negative x, this gives me negative 5x to the 5th minus 4x to the 4th minus 3x cubed minus 2x squared minus x minus 6. Right? They're all negative. I would have 0 negative roots. Okay? So hopefully that makes sense on rational zeros. That's really important. the Descartes rule of sign is nice because it helps us to find a starting point, right? Why plug in negative roots into this function? You're not going to have any, okay? So when I get my P and my Q, and I have my P over Q, I'm not going to plug any of those in to my synthetic division because I don't have any negative roots there, okay? So I want to make sure that I kind of work smarter, not harder. All right, guys?